Let me get started with a question that I got on Piazza. If you have more questions, feel free to add them on. So here someone had a question about how do we convert a string to the character, and can I explain the algorithm in more detail? And of course I can, so let me give that a good try. So the entire idea of this assignment is to show how you can use a queue to avoid recursion. So if you remember, we had this program when we first studied recursion on how to compute all of the permutations of a string. And so at the time, the algorithm was that if you had a string like this, and now you wanted to compute all the permutations, what you would do is you would lop off the first character. You would then compute all permutations of the tail. And then you would stick the first character in various positions. So, and that was complicated, and so this gives you a different way, maybe not a simpler way. So let's see how this goes here, and I'll just do it with an example. So I have a string, let's say ABCD. And for reasons that will become apparent in a minute, I will stick a vertical bar in front, and then I'll put it in a queue. So here's my queue. Right now the queue only has one element in it. And admittedly, now that doesn't yet sound so useful, but it'll be so in a minute. Now what I do is I loop around, and every time in the loop I take out the head of the queue. And so the motivation is the queue is stuff that I must work on. And I will take it out, I will make it simpler somehow, and then I'll stick it at the end of the queue so that later on I will again to get working on it. So right now it'll look a little bit artificial because the queue is now going to be empty because I've taken out the ABCD. And now let's see, what does the algorithm say? I have to put four things into the queue, namely A, B, C, D, B, A, C, D, C, A, B, D, and let me actually put them so that it looks more like a queue. I put them behind each other. So B, A, C, D, C, A, B, D, and D, A, B, C. So I'll get in a minute to exactly how we make these strings, but right now if you look at the strings, you'll see that for each of the four choices of behind the vertical bar, I pulled it up and removed it from the end. So now I have these four things in the queue. And I need to get to work on each one of them. And the reason to have the queue is because you can only work on one thing at a time. That way you stash away the things that you're going to get around to later. So now things start getting more interesting. Now I'm going to take the first one, take it out of the queue, and at the end I'm now going to stick in, now I only have three letters to worry about, so I'm going to stick in now I need to move to front, A, B, C, D, and then my queue gets longer, so I'm going to continue it on the next line here, A, C, B, D, A, D, and help me out here, BC. So these are strings that I still have to work on later, and they get stuck at the end of the queue. So next I'm going to take this one here and break it down in the same way, and I'm not going to go through the details right now because it just gets really boring. Maybe I should have done it with a shorter string. So in fact I did that on Piazza. I took a string with three letters and showed how to do it there. So be sure to work through that. So what's going to happen eventually? So eventually, if you look at the tail of the queue, you're going to get strings that are going to look like A, B, C, D. And maybe A, B, D, so later. A, B, D, C. Now, they're all the way at the end of the tail because one puts the late work to the tail. But eventually, you're going to be done with all of these complicated strings, the ones that have lots of stuff after the vertical bar, and you're going to get to these. So eventually, you're going to be pulling one of these out. It'll be gone from the queue. And now, there's only one way to change this. That's going to be A, B, C, D. And now the vertical bar has fallen to the end, meaning there's nothing to do afterwards. And then you can just return it. Now, you don't return it because you have to return a collection of all of the answers. So, strictly speaking, you put it into that collection and forget about it. And when the queue is empty, then you return the entire collection. That's the array list. So that's how the algorithm works. Try it out with 3 letters, and I think that way it'll be easier to see how it terminates, because that way you don't have to go through quite so many steps. But again, the way to think about it is that what the queue contains is partially completed work. So you pull out a bit of partially completed work, and because one item of work generates more than one item of work to be done in the future, that's where you need the queue. So for example, when we pulled out this one here, the A, B, C, D, it gave rise to 3 items, to these 3 items here that need to be done later. So if it was only one item, you could just keep working on it until you're done. But you have this fact that one item of work gives rise to more than one, and the queue is just a convenient way of storing it. Now I'm hoping that someone will say, do you have to use a queue? Could you use a stack? So let's assume someone asked that. I'm glad you asked. And yes, you could use a stack. It would work the same way. But somehow with the queue, it's nice that you first get all of the pretty complicated things and you break them down into simpler things, and you stick the simpler ones at the end, and then you have a few more complicated things, and eventually you get them simpler and simpler. You can try it out with a stack once you're done with the queue. It'll work the same way, but you'll see that the sequence of steps is different and maybe not quite as nice. Did that clarify anything, or do you have questions on it? Oh, let me address the issue that someone had on a more elementary level. How do I deal with all of that characters business? And so let's see what task we have to do here. So I have a string. I know that somewhere that string contains a vertical bar. How do I find it? Index of. An index of gives me the position of that vertical bar. And that's going to be some position I. Now, how do I find the stuff before here? Yes?
Can you just do a substring and do that?
Yeah, substring, right? So now I have to enumerate each of the characters that come after I. So at this point, it's going to be for k goes from I plus 1, k less than the length, k plus plus. And now I need to look at the kth character. There are 2 ways of getting at the kth character. You could use char at, or you could use substring from k to k plus 1. So which one is better? It's always such a pain when they're 2. Should you use char at, or you should use substring k plus 1? The rule of thumb is always use substring unless you have a specific reason not to do so. And that specific reason is usually one of 2. Reason number 1 is you want to use one of those nifty methods that are in the character class, such as is space, or is digit, or is letter. Those ones work with individual characters and not with strings. Reason number 2 is you want to change the character in some way, like you want to change an A to a B and a B to a C. In that case, you need to use with chars. If neither of those 2 reasons applies, then you should always use strings. because that way you always deal with strings, and a character is just a string of length 1 less concept in your brain to worry about. It would be nice if Java made that easier, and for whatever reason they don't, but it's not that hard a decision to make. So in this case, I would just say I have a substring here, then I have a substring here, I have a substring here, so 3 times substring, and now I have my 4 pieces. I have the thing before the vertical bar, I have 3 pieces behind, each of them stored in a string variable, and then I just concatenate them in a different order. So I would say, I think I called this one here S, then I would call this one here T1, C, and T2, say, and then I would say, what do I enqueue? And then it's q.add, okay, S plus C plus the vertical bar plus T1 plus T2. So in general, when you want to take a string apart and reassemble it in a different way, you can just use a sequence of substrings and pluses, and it'll always work. If you use charadd and it works for you, no reason to go back. I mean, it's just fine. But I'm saying if you don't know what to do, if you're still at the point where you're trying to decide how to do it, substring is something you need to know anyway, because when you have a string that's not just a single character but larger, you simply have to know about substring, and you might as well make substring a universal tool to take strings apart. All right, so I hope that helps. Let's see if we have another question here. Nope. All right, let's go to the slides, of which today have many. All right, so the easy part of today's lecture is these 3 collections, stacks, queues, and priority queues, and they're conceptually very easy. I mean, a stack, you use it if you are only interested in getting things out in opposite order in which you put them in. And so here's your stack of pancakes that, which if you think about it, is actually not such a great data structure for pancakes, because the cold ones stay on the bottom for a long time. Right? Maybe a queue would be a better data structure for pancakes, but for whatever reasons, then again, maybe you say the cold ones are lost cause anyway. You might as well eat them hot when they're hot. So if you think like that, then a stack is a great data structure. So you have these operations: push, pop, and is empty, and that's really all the operations that you have on a stack. A queue is the opposite. It's first in, first out. So the thing to keep in mind is the queue of customers. You stand in line. Adding happens at the end. Removing happens at the beginning. Unlike the stack, where adding happens at the top and removing happens at the top. And it's trivial to work with them. I don't even want to go through the slide. The adding operation is called push for historical reasons, and the removing operation is called pop, but those are just names. There's a way of peeking at the top of the stack without removing. That's not really an elementary operation. You could always simulate peeking by first popping and then pushing it back on. But hey, there it is anyway. There's a way of finding out whether the stack is empty or not, which you'll need in an actual algorithm. It sounds... I still vividly remember when I first saw stacks. I said, they're just like array lists, but bad. Right? With an array list, I can put things at the end. I can remove them from the end. With an array list, I can move them at the beginning, in the middle. Why would I want to use a data structure that can do so much less? It's just like saying, why would I want to trade in, my nice big car for a Yugo? And maybe you don't remember the Yugo. Anyway, we'll see when we talk about stack algorithms. Why stacks are kind of a useful way of describing certain simple algorithms. So queues are similarly easy to work on. Their operations are add and remove, like we're used to. You just need to remember that add always adds at the end, remove always removes at the head, just like when you're in the supermarket. Finally, oops, they're priority queues. I put the wrong photo in here. Sorry about that. I need to fix the image. The priority queue is one that removes elements in any, well, you add them in any order, and then when you remove them, you get the most urgent one. And so that would be like if you're an office assistant and you have a whole bunch of files on your desk, someone dumps them onto your desk in random order, and then as you work through your workload, you would pick the most urgent one and do that first, and then you would do the next most urgent one, and so on, until you're hopefully done. So it's not actually a queue. It's just the name is a little bit misleading, and again, it's simple enough to use. People add priorities, priority items in there with an add method. They get removed with a remove method. The one thing that's a little bit confusing about priority queues maybe is that the way priorities are sorted, that the priorities are given some value, and with the integers it would be the integer number, and the smallest number is the highest priority item. So that priority 1, which would be the smallest one, is the first one, priority 2 is the second one, and so on. And that's just a convention that one just needs to get used to. So lower priority numbers mean they're more important. Just like when you're saying, this is the most important, second most important, third most important, and so on. Now, in this example, we use integers in the priority queue. That's not what you would normally do. Normally, you would put in like tasks or something that where it makes some amount of difference intrinsically what they are, rather than just putting integers. I don't think we're actually going to get to any example like that in 46B, but in 146 you're going to see several algorithms where the algorithm has things that need to be done, and some of them are more urgent than others. So for example, to find the shortest path from one place to a bunch of other places, there's a well-known algorithm that uses a priority queue in that way. So I think right now you just need to see that such a thing exists. All right. Here we just have a cruel exercise to see that you can master the API. So let me put this into Piazza. Okay. So get out a sheet of paper and run through this code. All right, so let's see if I can do this real quick. So we have a stack. On the stack, we're pushing 1, we're pushing 3, we're pushing 2. So I'm drawing it this way so you can see what the top is. Now we're popping them off and adding them to a queue. So over here I have my queue, and so I put the head here and the tail here, and see what am I adding? I'm adding a 2 to the tail, then I'm adding a 3 to the tail, then I'm adding a 1 to the tail. Now I'm putting them into a priority queue, so I'll draw that just as a little bag here. And so I'm putting them all in, 2, 3, 1. And now when I take them out of the priority queue, they come out in priority order. 1 is the one that comes out first, then 2, and then 3. So the answer must be 2. And in fact, it was a total waste of time for me to even think about how they end up in the stack and in the queue. Right? Because in the end, they end up in the priority queue in some order, doesn't matter in which order, and out of that, they get pulled out in priority order. So let's see what people did in this. And everyone got this right. All right, so you know the API, and that's good. All right. I hope lots of you did realize that you could skip the first 2 steps and just look at the fact that the last one is a priority queue. So this is, of course, a great reservoir for quiz questions when you permute these things in various ways. If we did quizzes in the exam, you'd see one of those, but we don't. So who needs it? So I'll give you a couple of applications for which stacks and queues are useful. I won't do anything with the priority queue today. In CS46A, when people for the first time see a whole bunch of parentheses, and for the first time in their life maybe they need to deal with these expressions that, this long, and they had like 5 parentheses, there's this little trick that one teaches, how to make sure that parentheses are balanced. So at first glance you say, well, balancing parentheses, that's trivial, right? All you do is you count the number of open parentheses, in this case it would be 1, 2, 3, and you count the number of closing parentheses, they're also 3, so it must be balanced, right? 3 open, 3 closed. But of course it's not quite as simple. If you look at this expression here, it's not actually balanced because, or is it? No, this one is. But let's say I move this parenthesis here. If I put it here, or maybe a little bit more elegantly, at a place where you would expect a parenthesis here. If I put it here, then the number of opens and closed hasn't changed, but now this is definitely unbalanced because when you come to this point here, you have too many closing parentheses. And so the trick that one teaches is, whenever you find an opening parenthesis, you take an imaginary counter and you add it. So you say 1. Here, the closing one, you say 0. And now here you have to say -1, and that means you lose because you drop below 0. So the recipe has to be that at the end you reach 0, and in the middle you never go below 0. And I actually find myself doing that sometimes when I have a very long and complicated expression. I want to find out where did the parentheses not balance, and that finds the spot. So that's a simple algorithm, doesn't need a stack, of course. But what if you have different kinds of parentheses? Now, no actual programming language does this, but in math, some people do use round parentheses, and then when they have too many of those, then they use square parentheses, and when they run out of those, they might even use braces. So what if you wanted to check whether an expression like this was well formed? That's where the stack comes in, because what you would do is you would push the parentheses on a stack as you see them, and I'll just demonstrate that here. So I'll take the opening brace, then the bracket, then I see the parenthesis here, then over here I see this parenthesis, and now when you see a closing one, then you pop the stack and you see whether they match. So in this case I would pop this one, and yes, they match, so I was okay. Then I see the bracket here, and so I would compare it with what's on the top, and they match, that's okay. And then I see the brace here, and they match. So if, on the other hand, they were coming in a different order, then the last in, first out discipline of a stack would mean I would sense the mismatch. So the stack is kind of my memory of which parentheses are currently open. So that's an algorithm that's easy enough to program. And here, if this was large enough, you'd see it. Let's see why that's not. And so I'm not going to bore you with the details here. It's something that you could very easily program if you ever wanted to, except you probably don't. Why did I put it in the book? Because everyone else does too. And I tried to leave it out and I got complaints. So anyway, there it is. Here's a slightly more interesting reason for using stacks. And that has to do with the way that we do arithmetic. So as you know, you spend a few weeks of somewhere in middle school to learn that multiplication is stronger than addition. That when you write 3 plus 4 times 5, then that means multiply 4 and 5 first and then add 3. Why is multiplication stronger than addition? Was it the will of the Lord? No. It's just a human convention that someone at some point figured that using that convention means fewer parentheses. And it happens more often that you want to multiply first and add later than it happens the other way around. And so they somewhat arbitrarily said, we'll just make it so that multiplication is stronger. So, but it does mean that you do need parentheses. Now, at one point, this fellow, this Polish mathematician whose name I can't pronounce, figured out that actually parentheses could be completely avoided if instead of writing the operator in between the things that it operates on, if you write them before. So, and it looks a little funny because that's not what they taught you in middle school, but somewhere in an alternative universe, all kids in middle school learn not to write 3 times 4, but they learn to write star 3, 4. And then if I want to write 3 times 4 and add 5, then they would know to put the plus here and the 5 here. On the other hand, if they wanted to multiply, if they wanted to do this, if they wanted to add the 3 and 4 first, they would write plus 3, 4. And then they say, oh, we want to multiply the entire thing with 5. For you, it's strange because that's not what you're used to. But believe me, the children in that alternate universe are happier than you are because they didn't have to learn about parentheses. So, in fact, this scheme is so useful that when the first pocket calculators came out, that one brand of pocket calculators used that very scheme with a minor twist. They put the operators after and not before. So instead of writing plus 3, 4, you would write 3, 4 plus. And it's psychologically a little bit easier because usually you kind of have the numbers in mind and then you say, oh, I want to add them. And then you would use, then you say, okay, now I've added 3 and 4, and I want to, now my next value is 5, and I want to multiply those together. And so those calculators, here you see a photo of one, don't have to have a key for parentheses. And in fact, they don't even have to have a key for the equal sign because whatever it is that the latest result is, that's the result of the entire expression. So when Hewlett-Packard came up with this calculator, the marketing people called it the calculator that has no equal. I had a calculator like that, and within a few days, as a, 12-year-old kid or so, I learned how to translate algebraic notation into reverse Polish notation in my head. And to this day, that's the calculator that I use because I've gotten used to it. Of course, within a year or so, a competitor, Texas Instruments, just did the obvious thing and put the equal sign and the parentheses onto their calculators. And nowadays, people don't really do that anymore. But the Java virtual machine actually uses the same scheme to do operations. And when you take a course in assembly programming, you'll see why that's a really good idea. So, if you wanted to compute these these reverse Polish expressions, you would again do it with a stack. And I apologize for the bacteria font here, so I'll just demonstrate it with an example. So let's say that I wanted to compute 3, 4, 5 star plus. Here's how I would do it. When I see a number, I push it on the stack. I see another number, so I push that. I see another number, so I push that. I see an operator, so I'm now done with these 3 inputs. I see an operator. I pop the top 2 numbers off the stack, so now my stack only has 3. I take these 2 numbers, 4 and 5, and I multiply them because that's what my operator is, and I push the result on the stack. Now I see the plus. I pop the top 2 numbers off the stack, that's 3 and 20. Now the stack is empty. And then I push the result, 23, back on the stack. And there is my computation. Now, admittedly, it's not very likely that you yourselves, right this minute, want to evaluate reverse Polish notation. Yeah?
Can you do a problem with multiplication and division next to each other?
Sure. So do you want them next to each other, or you want them like interleaved?
Both, maybe?
Okay. How about I do one where I to say 3, 4 times 2 over. That way you see the order a little bit interleaved. So let me wipe out my thing here. So I push the 3 on the stack, I push the 4 on the stack, I pop them both off, multiply them, replace them with their product. I push the 2 on the stack, I pop them both off, and replace them by the quotient. So the reason this might be interesting at some point is people who implement a compiler. They need to know this kind of stuff because, like I say, internally a computer may use such a stack. So for those, it's an interesting algorithm. All right, just for the heck of it, just to gauge our love of reverse Polish notation. All right, clicker away. Okay, good. We have 6 votes already. 8 votes. Some of you must have a Hewlett-Packard calculator. All right, and so we have an overwhelming winner here, and yeah, that's just the right answer. All right, so this is easy stuff. That's good. Now I come to an application that is actually more useful, something that you might actually kind of wonder how one would do it, and that is how to evaluate regular old algebraic operations. So imagine that you had to write a program that does a pocket calculator-like thing where the input is a regular old algebraic operation, something like 3 plus 4 times 5. And now you would have to figure out what is the value. And you imagine that thing could be arbitrarily complex. And as with the, 3 plus 4 times 5 plus 6 minus 7 plus 8. Now, how would you write a program that does this? Yeah, at this point, your best bet would probably be to write a program that generates the Java program, compiles the Java program, runs it, and see the answer. Because there's no obvious way of doing it. So I'll show you an algorithm that deals with things like that. And it needs two stacks. You keep a stack for the numbers, and you keep a stack for the operators. And the twist is that, so when you see a number, you push the number on the stack because you don't really know what to do with it yet. So let's say you see the, do I know what input we have? Oh, 3 plus 4. So when you see the 3, you say, well, I don't know what to do with it. I put it on the stack. When you see the plus, you say, well, I don't yet know what to do with it. And the reason, of course, because you haven't seen the 4 yet, so you put the plus on the operator stack. Now you see the 4. And now at this point, you have everything together that you need to figure out the answer. And now what you do is you pop the top two numbers off the stack, combine them with that operator, and push the answer on the stack. That's a basic step in this algorithm, and that step is called evaluating the top. But you have to nuance that a bit because when you deal with different operator precedences, the fact that multiplication should happen before addition, you need to work a little bit harder. So let's see how that works. So let's look at an expression like 3 times 4 plus 5. So we see the 3, we push it on the stack. We don't know what to do with it yet. We see the star, we push it on the operator stack. We see the 4, and we put it here. Now we see the plus. And at this point, we now need to make a decision. We need to make the decision, should we evaluate the star, or should we also push the plus on the stack? And it depends on which of them is the stronger operation. So in this case, the multiplication is stronger, and therefore you want to do it. You just want to resolve it, so that's the 12 here. But think for a minute it had been the other way around, that it was 3 plus 4 times 5. At this point here, this would have been a plus. This one here would have been a times. Now at this point here, you see there's a plus on the stack, and you are having a star, and that means that that plus cannot yet be applied. That the star is also something that we don't yet know how to do because we're still lacking the 5. In that case, you would also have pushed it. So the idea is that you always push stuff on the stack that you don't yet know how to deal with, and when you find a stronger operator than what's already on the top of the stack, you need to push the stronger operator. Now how about parentheses? Parentheses are also one of those things that say that until you see the closing parenthesis, you don't quite know what to do, so you push the intermediate stuff on the stack. So let's see what we do here. So this is our initial expression. We see the 3, it goes here. We see the multiplication. Well, we don't yet know how to do with it. Now we see the parenthesis, and we push it. We don't yet know how to deal with it until we see the closing parenthesis. Oh, great. Well, it'll hopefully come back in a minute, huh? All right. All right. Well, while it's doing its thing, it's one of those algorithms. You just need to look at it for 5 minutes, and you'll see the basic wisdom. The idea here is that the stack is like your memory, and because you want to deal with things in a last-in, first-out fashion, that the innermost opening parenthesis matches the innermost closing parenthesis, the stack is the right data structure. The book now goes on with an actually kind of nice example on how you can escape from a maze by using either a stack or a queue of keeping track of decision points. So I'm just going to motivate it for a minute, but we're not going to go into detail. It's good to know that it's there, but it would take me too long to go through it, so that you really get the subtleties of it. All right. Okay. Oh, there we go. All right. So I'm just going to just show the picture so you'll get the idea. So the idea is that you are in this maze, and now you want to escape from the thing, and you kind of need to remember where it's still worth trying stuff. So when you're at an intersection, like here, now the way this algorithm works is you say, I'm going to push on a stack all of the paths that might be good to follow. So there's 4 different ones in this case, and you would push them all on the stack. And now they're on the stack. Now you would take any one of them, the top one, and you would start following it until you come to a new intersection. So that's the case up here when we are at a new intersection, and now we push 2 more of those choice points. Pop off one of them, that's this one here, and follow it. And that gets you here. Now that was a dead end. And now what you do is you pop off the next one. You now teleport yourself back to this point here, or you just retrace your path to get back there. And then you try this end here, which sadly is also going to be a dead end. And now you've kind of explored this path here. It led you nowhere. So the next one you get to try is this one. So that's the basic idea of it. It's and like I said, I'm not going to get into this. In 146, you're probably going to be seeing a bunch of these backtracking algorithms. And a stack is just a convenient way of keeping track of all of the decisions that you know you've partially made, but you still need to work off some of them. You could also use a queue. The algorithm would work equally well. It would just schedule them in different ways. All right. And in fact, I didn't give any code here. So I just wanted to raise that basic issue. That gets to the end of stacks and queues. You have a pretty nice homework with the queue that I think is a good example of using a queue for a real algorithm. Otherwise, just keep in mind what they are. It's pretty intuitive. And you're probably not going to be seeing much of them for the rest of the semester, just because they're so simple. It's not really worth doing much with them. All right, let's see. There was one more question that I noticed here popping up on the quiz. All right, so he says, suppose you push an integer elements 1, 2, 3, 4 in a stack in this order. So I'll do it 1, 2, 3, 4, and I'll make my stack grow upwards. Then I pop them off and add them to a queue. So I take the 4 and move it into a queue. Now it's at the end of the queue. I repeat that 3 more times, so they all end up at the end. And now, in which order do I remove them from the queue? I remove them in the order 4, 3, 2, 1, because with a queue you check the head of the queue each time. Okay, do we have any other questions? Is the output I want for the input word or I don't remember. Let me look. All right, so for the draft, I wanted to have a simpler output, but We no longer care because the draft is over. This was 7B, okay. Oh dear, what was the assignment? Can someone remind me what the assignment was so I don't have to look it up? Well, we have to write the sentence backwards.
You want the capitalization to begin.
Okay, then I don't understand the question. All I can do is give an example of what I want. So I mean, it's just a simple exercise to show that you can use a stack, right? So if you have a sentence like that, all I want you to do is you push these words on the stack. Now don't push the period, strip it off before. At this point here, you can pop them off, and you need to remember to capitalize the first one, or maybe not even push it, but just print it. And now I guess now you have to lowercase this one, right? Even though it doesn't make sense. And now you have your second sentence, you do the same thing. So you uppercase the first one, you leave all the others alone, but you lowercase the last one. And that's all that I wanted. I realize it's not tremendously useful. Yeah?
So I'm going to use the tester with the one word.
Oh, so what if I have one word? Ooh. Okay, that is a much better question. I have no tester with one word, so let me answer that question. Yeah, that is a really good question, because then it's not clear which of the two rules applies, right? Should you lowercase it or should you uppercase it? So you can assume that each sentence has at least two words.
It could be a question mark or a period. Is it one
It's a period.
or just a period?
It's only a period. Yeah, nothing else. It's just a dumb assignment to make you use a stack for something. I mean, it has no practical use, right? No one's going to try this on Alice in Wonderland. Although you could see what comes out of it. All right. Did we maze escape? I see. So here's here's someone asked what I think is an interesting question, and that is how one would take this whole algorithm and make it like print the path, not just get the robot out, but to actually print a path. And that's certainly doable, but you kind of have to keep an intermediate result of everything that so far was successful. I didn't add that into the algorithm in the book because that would make it quite a bit more complicated. On the other hand, that would make a great assignment, which I may actually have already as an assignment. I'll double check if I have it, otherwise I'll make it into one. Now, but it should be within the abilities of someone who's gotten this far to, if you have a couple of hours, to figure this out, to come up with an algorithm that not just makes the robot escape, but that keeps track of the path of the shortest path that is needed for escaping. The algorithm, the way that I've outlined it, does not keep enough information to do that. All right.